for this nice conference in these hard times. Right, so I will be talking about non-associative Skew Laurent polynomial rings. So here's an outline of my talk. So I will start with some background, just a bit short, and a motivation. I mean, why even consider non-associative things? I will talk a bit about the classical setup of Skew Laurent polynomial rings, what they are, just to remind you. And then we'll go into this uncharted water of non-associativity. And I will mainly talk about results on ideals such as simplicity. And then I will be talking about Hilbert's basis theorem for these kinds of rings. So just a short background and motivation then. So Skew Laurent polynomial rings or Skew Laurent series rings are non-commutative rings which have a skewed or twisted multiplication. And it seems that Hilbert was the first one to actually consider these kinds of rings. So he was interested in constructing an ordered division ring which was not commutative. So he sort of skewed or twisted the multiplication of a certain Skew Laurent series ring. And since Hilbert introduced these, they have appeared as typically as universal enveloping algebras of Lie algebras, quantized coordinate rings of algebraic varieties, group rings, cross products, etc. And they're, for instance, used in coding theory. There are some related rings which are called Ure extensions, and they were introduced some 30 years later by the Norwegian mathematician Øystein Ure. And Ure was interested in constructing, in sort of the most general way, a non-commutative ring. What should that mean? Some years recently, some colleagues of mine realized that within this structure with extensions naturally lies some kind of non-associative structure. So non-associative Ure extensions naturally arise from these associative Ure extensions. And I thought that they were kind of nicely defined and so on, and you could you could extend some results to the non-associative setting. So I thought, what about non-associative Skew Laurent polynomial rings? What should that be? And hopefully I will convince you that they could be useful in this talk. So as I said, we've mainly generalized results on ideals, namely simplicity and Hilbert's basis theorem. And to me, this came with some surprises, which I thought had nothing to do with associativity. So we'll tell you about that in the talk. So let us now, right, so first I should say that this is based on a joint work with a colleague of mine, Johan Richter, at Bäck Institute of Technology in Sweden. It's a preprint. All the rings in this talk will be unital, but of course not necessarily commutative. I will explicitly say if they're associative of or non-associative. Okay, so let us dive into the classical setting now. So in the classical setting, one can define Skew Laurent polynomial rings in this sort of abstract way. So Skew Laurent polynomial ring is a ring which contains a subring, and this subring in turn contains the identity element. And we have some element x, which should be invertible. And then the ring should satisfy the following three axioms. So the first one is that it should be a free left-arm module with this basis, just as for ordinary Laurent polynomial rings. And then we want the multiplication to be twisted somehow. So whenever I multiply x with some element in the base ring R, I should get back some element R times x, and also the other way around. So this twists the multiplication, and we also require the ring to be associative. So that's it. Now, this doesn't really tell you how to go about and construct these rings. So there is a more concrete definition as well. So you start with an associative ring and an automorphism on this ring. And that's it. That's the basic data. And then the generalized Laurent polynomial ring is just a set of formal sums. You use just pointwise addition, and the multiplication is twisted like this on monomials and then extended to all polynomials. So this is just a Laurent polynomial ring with a new multiplication. And then inside this ring also lives the generalized polynomial ring. Now, it turns out that the generalized Laurent polynomial ring is, in fact, a Skew Laurent polynomial ring. So this is the way to construct them. And also the other way around. I mean, each of these Skew Laurent polynomial ring is isomorphic to one of these concretely constructed rings. So this gives you a nice correspondence between these two definitions. So you know how to construct them and you know what they are. Just some super simple examples. So the ordinary Laurent polynomial ring is a Skew Laurent polynomial ring in which multiplication is not twisted, right? One can do something a bit more advanced. So you can take complex conjugation. That's an automorphism. And so you can skew the multiplication on ordinary Laurent polynomial rings with complex conjugation. And for instance, I mean, the first sort of nice result I learned about in algebra, I think, was that you could construct the complex numbers as a quotient of the ordinary polynomial ring over the reals as follows. So you didn't have to say anything about this strange imaginary number. And then it turns out that you can do the same thing with the quaternions if you instead use a skew polynomial ring and twist it by complex conjugation. However, as far as I know, the story sort of ends there. So there's no construction, what I know of the octonions, the centennions, and so on in this fashion. Another example would be the quantum torus. So it's the free algebra on two letters, x and y, which are invertible, modulo this ideal. And this is then isomorphic to an iterated Skew Laurent polynomial ring. And there are, of course, many more examples. Okay, so let us dig into this non-associative setting now. So by a non-associative ring, I think we mean a ring which is not necessarily associative. The associator is a function which sort of measures the non-associativity of elements in the ring. And whenever I write capital letters in the associator, I mean finite sums of associators. There's something called the left nucleus. So this is the set of elements which associate with everything from the left. And similarly, you can define the middle nucleus and the right nucleus. You need some kind of concept of a non-associative R module. So the way I define this is just as an additive group with a biadditive map, which is closed. So this is just as in the ordinary associative setting, only that you forget about the associativity condition. Okay, so let us now go into the definition of non-associative Skew Laurent polynomial rings. And I will sort of motivate this afterwards, why this strange definition. So I've bold-faced here the things that have changed from the associative setting. So now you're, of course, interested in a non-associative ring. The first axiom is just as in the associative setting, you still want it to resemble a Laurent polynomial ring. The second condition is also the same as in the associative setting. You still want it to be skewed in the same way. But you replace the associativity condition with this seemingly strange and arbitrary condition that X should associate with everything from the left and in the middle. Now, in order to actually construct these things, you do as in the associative setting, but you change some things. So what you do is that you now can take an arbitrary non-associative ring, and instead of taking an automorphism, you take an additive bijection that respects 1. And then you consider again just the set of formal sums with pointwise addition and this kind of skewed multiplication. And of course, the generalized polynomial ring lives inside here as well. So in order to motivate this kind of abstract definition, it is as follows. So in the associative setting, one can note that if you allow this automorphism merely to be an additive bijection, you still get some kind of ring structure on the set of formal sums. So this ring structure is very much like a Skew Laurent polynomial ring structure. You have the same kind of multiplication, but you now have more choices, of course. The sort of point here is, however, that this ring will in general not be associative anymore. So the question is sort of how should you change the axioms in this abstract definition in order for these two kinds of rings to correspond to one another. And it turns out that you should do it as I've stated here. So that's why you have this strange third condition here, which replaces associativity. So indeed, all of these generalized Laurent polynomial rings are Skew Laurent polynomial rings if you use X as your capital X. And also the other way around, each non-associative Skew Laurent polynomial ring is isomorphic to one of these. So they correspond to one another just as we wanted. Some basic results. So for non-associative Skew Laurent polynomial rings, the base ring lives in the left nucleus precisely when the ring is associative. And the indeterminate X lives in the left nucleus. So it's associated with everything from the left precisely when this map sigma is an automorphism. And the ring itself is associative precisely when the base ring is associative and this sigma is an automorphism. So some sort of generalizations of the examples that I had in the associative setting are as follows. So an ordinary non-associative Laurent polynomial ring is an example. Also, you can define on the complex number some kind of Q-deformed version of the complex conjugate. And this is an additive bijection that respects 1. So you get now non-associative Skew Laurent polynomial rings twisted by this Q-deformed thing here. Also, if you want to, you can consider now octonionic quantum tori. So one way to define this is to take the R tensor product of the octonions and the usual quantum torus over the real numbers. And then it turns out that this is precisely isomorphic to a non-associative Skew Laurent polynomial ring. And this is, of course, not associative as it contains the octonions. Right. So some more examples. So any anti-automorphism is a natural example of an additive bijection that respects 1. So they naturally give rise to these kinds of non-associative Skew Laurent polynomial rings. An anti-automorphism is, of course, an automorphism precisely when the ring is commutative. So these rings are associative precisely when the base ring is associative and commutative. And a further example of an anti-automorphism is an involution. So if you have a ring with an involution, a so-called star ring, you will naturally get many kinds of examples of non-associative Skew Laurent polynomial rings. So take, for instance, the complex matrices with conjugate transpose. That's a star ring. And you can now skew the multiplication and get some kind of non-associative Skew Laurent polynomial ring. The classical algebras in the Cayley-Dickson construction naturally contains an involution, namely the conjugation. So they also give rise to these kinds of skewed non-associative Laurent polynomial rings. They're associative precisely when the base ring is the real numbers or the complex numbers, but if you put, for instance, the quaternions, you get something which will no longer be associative. So I thought, well, can you construct now, for instance, the octonions in a similar way to the complex numbers and the quaternions by using this construction? And unfortunately, I couldn't do it. So I, for a long time, thought that it would be this ring, naively guessing. So this was an 8-dimensional real algebra, but it contained 0 divisor, so it was not the octonions. But maybe there is some other kind of construction, I don't know. So that's a question I have. Right. So let me talk a bit about simplicity. So I say that a map has infinite order if you cannot raise it to power to get the identity map. And for commutative non-associative division rings, if your sigma has infinite order, then you can show that the following Skew Laurent polynomial ring is always simple. So if I go back to one of my examples here, the complex numbers with this generalized complex conjugation, this will be simple as long as Q is not equal to plus minus 1. So Q is equal to 1, you get the identity map. Q is equal to minus 1, you get the ordinary complex conjugate. And you can also prove a version in the other direction. So if your map really has finite order, then you can always find two-sided non-trivial ideals of these non-associative Skew Laurent polynomial rings. So for instance, getting back again to our example, it is never simple whenever Q is equal to plus minus 1, since then you can then always find this non-trivial ideal. So at least in this case, as simple means as non-associative. And for star rings, you can always find, non-trivial two-sided ideals because you just raise to the power 2 to get the identity map. Right. So I'm going to finish up with Hilbert's basis theorem. So let me just remind you what this is in the classical setting. So a family of subsets satisfy this ascending chain condition if you cannot find a truly infinite chain of subsets from this family. And element is maximal if it's not contained in any other element. So in the non-associative setting, you can prove the following. So these conditions are all equivalent. Ring satisfy the ascending chain condition on either its right or left ideals. All non-empty families has a maximal element, and any right or left ideal is finitely generated. So this is precisely as in the associative setting, only generalized into the non-associative setting. And rings which satisfy them on the right or left ideal are still called Noetherian. Right or left Noetherian. They satisfy both conditions. They're simply called Noetherian. So in the classical setting, the classical Hilbert's basis theorem says that if you have an associative commutative ring, you can lift the property of being Noetherian to the ordinary polynomial ring. So it's of course named after Hilbert, who considered a version of this. I think he considered homogeneous polynomials. And this theorem generalizes into the non-commutative setting. So if you have an associative ring and sigma automorphism, you can lift the property of being right or left Noetherian to the skew polynomial ring and the Skew Laurent polynomial ring. So that's quite nice that you can lift both these properties. So what about the non-associative setting? So here was at least a surprise to me. Well, it turns out that you can lift the property of being both right and left Noetherian to Skew Laurent polynomial rings. Fine. But then it turns out that you can only lift the property of being right Noetherian for skew polynomial rings. So this was a bit surprising to me, that sort of this non-associativity distinguished between left and right, but not the non-commutativity, which you would expect. So when I said that you can only lift the right Noetherian property, I mean that there's also a counterexample for a left version. So there is a a left Noetherian ring in which the corresponding skew polynomial ring is not left Noetherian. So in fact, I think this R is even associative and commutative, and right Noetherian as well. So actually this is an example of a ring which is right Noetherian but not left Noetherian. Let me just finish off with something about Skew Laurent series rings and skew power series rings. So you can play this game also with truly infinite sums. So you can consider skew power series rings, and you can consider Skew Laurent series rings just as in the associative setting, but now you only have a map which is an additive bijection, not necessarily an automorphism. So everything is as in the associative setting, or as I said in the beginning. Now we have infinite sums, and here you can prove at least for associative ring, or sorry, in the classical setting, I should say, you can prove both a right and left version of Hilbert's basis theorem. However, in the non-associative setting, we have so far only been able to do it for an associative base ring and for right Noetherianness. So I have no clue if it's possible to do it for non-associative base rings, and if you can also prove a left version of this theorem, or if there are in fact some kind of counterexamples. Right, so I think I finished a bit earlier than I thought, but thank you very much for staying with me.